Hey everyone, this is Mr. Mott. What we're going to do is go over some notes on our heat labs 1, 2, and 3, starting out with heat lab number 1, which is mixing equal amounts of hot and cold water. Okay, so in our example, we have 50 grams of cold water and 50 grams of hot water. Okay, we have TI, which is our initial temperature of our cold at 20 degrees, and our initial temperature of our hot water at 80 degrees. So in the lab, we would have thermometers uh, in both of these. So we'll kind of draw in some thermometers. And then what we're going to do is mix these two things together. So typically we would mix, uh, pour one beaker or one cup into the other. Wouldn't matter which. You could also just pour them into another cup as well. So let's say that we had a third cup and we were going to pour these two things together. So we'd pour them together, and we'd have both thermometers in there as well, recording the temperature. And so one neat thing that would happen in the lab is that we would see, since the cold water started out at 20, because it's mixing with something that is hot, the temperature would go up. Whereas if we were noticing the hot water starts out at 80 and you're mixing with something that's cold, so the temperature of the hot water would actually go down. Okay, and the final temperature of this mixture would be 50 degrees Celsius. Okay, and so that would be the final temperature for both the hot and the cold water, because when you take something that's hot and something that's cold and you put them together, they will eventually become the same temperature. Okay, so that's sort of the basis of it. And from here, what we're going to do is sort of draw a graphical representation of what we should see. Okay, so in our graph, okay, so we have a little graph here. So we'll start out with a little spot here for initial temperature of our cold. Okay, so our initial temperature of our cold water, which was 20 degrees. And we would see a graph going something like this. And for the hot water, starting up here, so we'll write Ti of the hot, so the initial temperature of the hot, at 80 degrees. Okay, and so we would see that going here. Okay, now despite my picture, which may not be that symmetrical, what we should see is that the final temperature, T final, should be at 50 degrees. Okay, and so if I kind of draw a line straight across here, this is where T final would be. And what we could do then is calculate your change in temperature. So your change in temperature is given the symbol delta T. And delta T is always T final minus T initial, okay, no matter what. So if we look at and try to calculate the change in temperature of your cold water, we would take, so your T final, which is 50, minus your initial temperature. So the initial temperature of the cold water is 20 degrees. Okay, and so 50 minus 20 would give me 30 degrees. And again, we also know that the temperature of the cold water, that temperature went up. Okay, so it started out at 20 and went up to 50. If I do my change in temperature for the hot water, so delta T for the hot water, I'm going to take my final temperature, which is again, so T final, which is 50, minus the initial temperature of the hot water, which was 80. So 50 minus 80 gives you negative 30. And so at this point, you might ask yourself, is that negative significant? I think it is, because the hot water started out at 80 and it went down to 50. So the fact that the temperature went down gives rise to this negative symbol, or I guess that's how you say we might keep track of the negative symbol there. Okay? So there's a lot to be learned from heat lab number 1, mixing equal amounts of hot and cold water together. Okay? So we learned that the final temperature, the T final, is equal to the average of your initial temperature. So I would say, to calculate it, it's the initial temperature of your hot plus the initial temperature of your cold. So plus Ti of the cold, and then divided by 2. Okay, so that's an important idea. The other thing that we could also say is that your change in temperature of your cold water is going to be equal to the negative change in temperature for the hot. And that's true whenever you're mixing equal amounts of hot and cold water or equal amounts of the same substance. Okay. So from here, what we did is that we looked at heat lab number 2. Heat lab number 2 was mixing unequal amounts of hot and cold water. Okay, so let's take a look at what that looked like. Okay, and we'll give a little title here. Heat lab 2. So this was unequal amounts of hot and cold water. And what we wanted to see was, by changing the mass, do we get different results? Okay, so we kind of did two different little mini experiments here. Okay, so we did one where we had more hot water mixing together, and then we had another one where we did more cold water. Okay, so just for our concrete learners out there, so more cold water means I might mix, say, 100 grams of cold water and maybe 50 grams of the hot, for instance. We would mix different amounts, different enough so you would see an impact if mass was important in terms of how much heat it can hold. For instance, if we did more cold water, okay, or excuse me, more hot water, this might mean I could flip it, 100 grams of hot and maybe, and maybe 50 grams of the cold. Okay. Now, what we could think about in two ways is make a prediction here. We could say, what do I think that final temperature is going to be when I mix more hot water versus more cold water? Do I think it's going to be the same as heat lab number 1? Or do I think it's going to be different? And if it's going to be different, then if I mix 100 grams of hot water, 50 grams of cold, do I think that the final temperature will be closer to the initial temperature of the hot or the initial temperature of the cold? And then as another way of thinking about it, what would that graph look like? Okay, so the results of the lab are something like this. Okay, I'm going to draw my axes here and scoot that over. And then for the more cold here. So here's kind of what my graphs would look like. If I had more hot water, this is what my graph would look like. Okay, with your final temperature being closer to the initial temperature of your hot. Okay, and let me just go ahead and draw this. If I had more cold water, my final temperature would be closer to the initial temperature of the cold. All right. Not working the way I want. Okay. So close enough. All right. So that's kind of what it should look like. And the reason behind this is because if you have more of a substance, it can contain more heat. Okay? And this shouldn't be sort of a foreign idea to you because if we were to if you were at a sink and you were turning the two handles, one that was hot water, one was cold. If you turn a lot more hot compared to just a little cold, well, the mixture of water coming out is going to feel more hot. And if you turn on the cold all the way and only the hot a little, overall it's going to still feel pretty, cold. And so really, this idea isn't new as long as we think about it in that context. Okay. Let's see if I can fix how this was located there. There we go. All right. So from Heat Lab 1 to Heat Lab 2, we figured out that mass is important in terms of heat transfer. Okay. If you wanted to be able to figure out your final temperature, the formula is a little bit more complicated. It has to do with percentages. Okay, so you could do this in terms of percentage, or you could say it would be how you would figure out, you would say, okay, mass of my hot over mass total, okay, times the initial temperature of the hot, plus mass of your cold over mass total times the initial temperature of the cold. And this should make sense because, again, if you have a lot more hot compared to cold, that's going to come out differently in the faucet versus if the masses were more close to each other. Okay. For Heat Lab number 3, what we did is that we changed the identity. Okay, so Heat Lab number 3, we said, what if we had equal amounts but different identity or different substances? Okay, so what we did is that we had a cup. In that cup, we put some cold water. And the amount of cold water had to match the mass of our solid. Okay, so a lot of times we have pieces of aluminum or copper. So if this weighed 58 grams, then we put 58 grams of water, cold water, in here. Okay, so whatever the mass of our metal was, we took the same mass of water. And what we need to do then is heat up our metal. So what we did is that we put it in a hot water bath. So we had a pan. Let me just kind of move this over here a little bit. We had a pan and we put our metal in the bottom. That didn't work out so well. There we go. All right. And in the pan, there was hot water. So we took our metal and we put it into a pan with some hot water. We left it in there for about 5 minutes. Okay. We had a thermometer in the hot water. And after 5 minutes, we assumed that the initial temperature of the metal, okay, so the TI of the metal is going to be the same as the temperature of the water. Okay. After 5 minutes, then we took the metal and we put the metal into the cup. Okay, so let me move this over. Okay, try to move this over here. There we go. So after 5 minutes, we put the metal into our cup. And the metal is really hot now. So the metal is releasing energy, releasing all that heat that it got by being in the water. Okay? And what we did is, again, we kept track of the temperature. Okay, so what was the initial temperature of the metal, what was the initial temperature of the metal, what was the initial temperature of the water, then what was our final temperature when we put them together. And what we were trying to see is that, are we going to get a different result compared to Heat Lab number 1? Heat Lab number 1, again, was where the final temperature was the average. Well, graphically, this is what we noticed. Okay, so graphically what we noticed was that, there we go. Graphically what we noticed is that the temperature of the water didn't heat up very much, and the temperature of the hot metal went down a lot. And so my final temperature was a lot closer to the initial temperature of the cold. Okay, so this is what our graph looked like. And that shocked a lot of people because the metal was really hot and the water was pretty cold. And so this is usually pretty unusual. But either way, whether it was closer to the cold or closer to the hot, we did not get the same results as heat lab number 1. Therefore, we know the identity is important. And so that's the important thing about heat lab number 3. Okay? So from here, what we did is we put together some notes about what are the things that affect heat transfer. Okay? So we know, for instance, that heat from our labs is affected by mass. We learned that in heat lab number 2. It's affected by identity, which we learned in heat lab number 3, and the change that things are going to change temperature a little bit differently, so we need to keep track of our change in temperature. Now, this idea about the identity is given a different term in science. We're going to put a little parentheses around it. This term about identity is given a different sort of term, and it's called specific heat. Specific heat tells you how quickly something is going to heat up or cool down, and also can be used to identify what that substance is. Okay? Some abbreviations to throw at you. Heat is given the abbreviation Q. M is going to be our abbreviation for mass. Okay. Specific heat has a few different designations. We're going to abbreviate it as C. You'll see it also as a capital italicized S. And then change in temperature, or change in temperature is delta T. So I've already kind of abbreviated that. Okay, there we go. In terms of some units for these, heat has a few different units. It could be calories, or it could be joules. Either one of those are ones that we use. Calories are most often used in the food industry. Mass, the units are going to be grams. Specific heat, the units are a little bit more different, and we'll kind of explain that. These units are your unit of heat. Most oftentimes it's going to be joules over grams degrees Celsius. And then the last one for temperature was degrees Celsius. Okay? And I'm just going to change the color of these so they're a little bit different. And let's make them, I don't know, purple. All right. So heat depends on all these things, and now we have a formula where we can do some calculations with this. But before we go any further as far as our calculations, let's just sort of focus on this idea about specific heat. So I'm going to give you an example of what we mean by specific heat. Let's say that we have the specific heat of water. The specific heat of water is 4.18 joules per gram degrees Celsius. It's written like that. And this is a very, very high specific heat, which we're going to learn more about. But what this really means and why the units are sort of more complicated than most, what this means that our 4.1 joules of heat energy, so 4.18 joules of heat energy are needed to raise 1 gram of a substance 1 degree Celsius. Okay, clean up my writing there a little bit. So when we look at a value of something and it says it has a specific heat value, joules per gram degree Celsius, we don't put the ones in the denominator because we know ones in the denominator don't change the value. But what it does mean is that it tells you how much energy is needed to raise 1 gram of a substance, 1 degree Celsius. And like I mentioned, there's lots of different implications of this. The specific heat will tell you how fast something heats up and cools down. What we're going to learn a little bit later is that water takes a long time to heat up, but it also takes a long time to slow down because its specific heats are very high. Most metals are going to be less than 1 for their specific heats, and so they're going to tend to heat up quickly but also cool down quickly. All right. Thanks for watching our video on our 3 different heat labs. Hopefully that's helped clarify how heat is transferred and all the different things that affect it.